Hello and welcome to episode 14 of CS350 Online. I'm your host, as always, Leslie Eisted, and on today's episode, we're going to discuss methods for improving the performance of multi-level paging, and we're also going to discuss how OS 161 has implemented its virtual memory, which will be super relevant for when it comes time to implement Assignment 3. But first, let's talk about our OS of the day. Now, this one is a personal favorite of mine. It's SunOS, as it was originally known, or Solaris, as it is known more recently. This was released in 1982, and it's a product of Sun Microsystems. Now, for those of you who see the name Sun Microsystems and you're like, this kind of sounds familiar, but I don't know why, it's because Sun was one of the biggest companies for computing hardware and software in the world, like IBM or Microsoft, employing, I think it was close to 100,000 individuals around the globe, and they are gone. They have been officially acquired by Oracle. I want to say that was about 10 years ago, but the death of Sun began right around 2003. I was actually working at Sun at the time, and while I was working there, they actually laid off 10,000 people. Now, lucky me being a co-op student, of course. Co-ops don't get laid off because we're cheap. Anyways, Sun stands for, by the way, Stanford University Networks, because this, of course, was a startup out of Stanford. Now, what is SunOS? So SunOS, or Solaris as it is known more recently, is a closed source distribution of Unix version 7/BSD. This particular operating system is actually very, very popular. So it was one of the first versions was actually made popular by Lucasfilm. They used it for a nonlinear editing system. Because in about 1983, their desktop GUI was actually considered high-quality graphics. Now, as someone who has worked at Sun and used Solaris for many, many years, I can tell you that maybe they let that get to their head, because I don't really feel like they actually updated the desktop graphics since 1983. But hey, I wasn't exactly using Solaris for the graphics environment. So one of the things that Sun is most known for, of course, is their networking support. I mean, Sun, Stanford University Networks, it was for a big part of their life, they were about improving networks and improving network support and so on. And they have a famous slogan, and of course it slips my mind, but it's something like, the computer is the network. I don't remember. All right, so you've got a Unix-based operating system with significantly more networking support than the other Unix-based and other consumer operating systems of that time. Now, why did they make the change from SunOS to be calling it Solaris? My understanding of why it started to be known as Solaris is this happened right around the time where Sun introduced 64-bit. So back in the early 90s, late 80s, people were starting to realize in data centers and scientific communities that 32 bits wasn't enough, because you couldn't address all the memory that you actually needed. And so several companies actually went forth under the mindset, hey, we need to introduce 64-bit architecture so that data centers, which there weren't that many of, but scientific computing, could actually address the memory that they needed to. And Sun created the 64-bit SPARC architecture, and they were actually the first company to market with the 64-bit CPU. And of course, they created the operating system modifications necessary to utilize that 64-bit CPU architecture. And I believe that's right around the time where they renamed SunOS to Solaris. Solaris sounds a lot better too. So yes, you can thank Sun Microsystems for the popularity of 64-bit and many other things as well. Like Java, if you're a Java developer, Java's not from Oracle. Java's from Sun. Always has been. So as I said, Solaris was actually exceptionally popular. And in fact, when I was an undergrad at UW, that's actually what the school servers ran. It was a bunch of Sun hardware, and we ran SunOS and Solaris. And so we were using a more traditional Unix-based operating system. And it was every machine was that. In fact, it was, you didn't get a Windows account. They actually resided on a different kind of network. And you only got a Windows account if you took a course that used a Windows machine. And so few courses in math and CS would actually require that. So you usually had to take a course from another faculty to get Windows access. All right. So if you're wondering what happened to Sun, so Sun manufactured their own hardware, the SPARC architecture, which of course was also part of the acquisition by Oracle. And this hardware was very expensive. It worked really, really well. And SPARC's neat because it's a RISC CPU, so its assembly is very, very easy to work with. It's actually very, very similar to MIPS. So the hardware was really great, but the hardware was very expensive. And the operating system was also very expensive. And because it wasn't like a general operating system, you had to pay Sun for support. There was no like third-party support people. So you had to pay Sun for very expensive hardware. You had to pay them for a very expensive operating system. And then you had to pay them to support those machines. And it became really, really costly. And people in the late 90s, early 2000s started realizing that you could march your ass down to the Fry's. That's the big computer store in California. Lovely place. Or you can march yourself down to Canada Computers or whatever computer shop you have locally, and you could buy a bunch of consumer grade hardware, and you can stick it all together into a cluster of machines that would be just as fast as the architecture you purchased from Sun, except it would cost a fraction of the price because it was standard consumer hardware. It was relatively easy and cheap to repair, and it could run standard operating systems like Linux or Windows or whatever you wanted. And so the cost of do-it-yourself servers actually got so cheap that everybody was doing it. I mean, people were making servers out of like PlayStations, and it worked. And so Sun kind of caught on to that a little too late. They did start doing that, like actually making Sun branded machines that were made of consumer parts. They caught on a little too late and they ended up dying. Now that's probably not the whole story, but that's the story from someone who was there when this actually started, their downfall. It was, by the way, a wonderful place to work. Was there any talk about cloud computing at the time? Yes, actually there was. So when I was at Sun in 2003, one of the projects that I was working on was actually, I'm not sure if the word cloud was thrown around too much, but the concept of building this cluster of machines that we could then use for like a global storage device was definitely one of the things that I was working on. But they didn't talk too much about the cloud, although the origins of the cloud were starting at that point. Sorry, for those of you, that was actually a question on Twitch there. All right, so where did we leave off? So last episode, we finished discussing multi-level paging. So that was a weird thing. So we talked about single level paging, and the whole point of this single level paging was the idea that we want to eliminate external fragmentation, because internal fragmentation for a paged or segmented memory isn't really a big problem, but external fragmentation can be a big problem with segmented memory. So we wanted to eliminate that, and we made the observation that if you have allocations of different sizes, that's where the external fragmentation problem actually arises from. So let's make sure that each of our allocations is exactly the same size, and that way we have no external fragmentation. And that's kind of the idea for where paging comes from. You subdivide physical memory into these equal-sized frames, and you subdivide virtual memory into equal-sized pages, and then instead of requesting contiguous large chunks of memory, you just say, give me any 7 frames, and they don't have to be contiguous in physical memory. Now, the downside of this is that when you have each page mapping to some random frame, you're going to actually have to create a page table to actually store all of that information. And as I pointed out before, the page table actually has to contain an entry for every possible page of the virtual memory, not just the ones that you are using. Now, in our particular example in these slides, our address spaces are a single contiguous block. So we could technically have a smaller page table, but that's not the reality of how page table or address spaces are actually arranged. We know that you've got code segment, and then a little bit further away you've got the data segment, and then further away still you've got the stats segment, and there's a whole bunch of empty pages in between. And so in order to create a page table to represent that particular address space layout, you actually have to have a page table where every single possible page has an entry, and we simply use that valid bit to indicate whether the page is actually in use by the address space or not. And we talked, of course, about the various formulas that you can use to compute whether or not, or how many pages there are, how many frames there are. We had formulas and techniques for actually performing the address translations, and I'll let you review those in the slides yourself. But one of the biggest observations we made is that this single level page table is actually really, really big as you increase the number of bits we use for virtual memory. For example, in modern systems which use 48-bit virtual addresses, our page table would actually be 256 gigabytes. And considering those page tables reside in the kernel of the operating system, we suddenly realized that this is not feasible. And so what we want to do is we wanted to find a way to reduce the overall size of the page table, but we also wanted to reduce the number of invalid entries in it, which was the whole idea behind multi-level paging. We're simply going to create a hierarchical table where the leaves actually contain the page to frame mappings, but we're only going to create subtables in the tree if there's at least one valid entry. So if there's no valid entry in that subtable, don't bother creating it, which actually ends up reducing the entire size of the page table, and it reduces the number of invalid entries you're going to find. And we gave you, again, a number of formulas for how to actually, and I know they're not in the slides, I gave them to you handwritten, but I gave you some formulas for how to compute how many levels there were and so on and so forth. And I'll make sure that the virtual memory guide gets posted to Piazza if it's not there already. Now, the one interesting thing about the virtual memory implementation of multi-level paging is that at the end of the day, the address translation is completely the same as it was for single-level paging. The only difference is how do you actually arrive at the frame number. So with multi-level paging, you've got to start at that root or the directory, and you've got to actually traverse this tree until you get to a leaf, and you finally get the frame. So you could have to go through 2, 3, 4, 5 different tables before you finally get your frame number. And since all of those tables are actually in memory, that's actually a lot of additional memory reads you're going to have to do just to do an address translation. Now, one of the interesting things to point out about multi-level paging is it's not universally better than single-level paging. In practice, it's better. But you can construct an address space where the multi-level table would actually be larger than the single level. So we don't want that to happen, obviously, but that is entirely plausible. And you could actually compute that. At what point does the multi-level table for an address space end up being larger than the corresponding single level table? That's kind of an interesting exercise you might try. And for those of you wondering, everybody always asks, what's in my cup? What is that pink stuff you're drinking? This is not my usual drink because every grocery store is out of my usual drink. So this is, I think it's like blood orange pomegranate something. I don't know. All right. So at the end of last class, the last episode, I actually gave you a couple sample problem pages to try. And why don't we take a few minutes then and actually take up the solutions to those two problems. So let's start with the first one. And if you're sitting at home right now, this is the problem known as paging. Just get one note up here. All right. Of course, I forgot to turn my tablet on again. That always happens. There we go. All right, so what we've got here is we have a 32-bit physical and virtual addresses, and our page size is the standard 4 kilobytes. And we're saying that a process P is running, but P only uses 128 kilobytes of virtual memory contiguously allocated. And we've shown the first 5 entries of P's page tables below. So the first question is, what is the total number of entries in P's page table? Okay, well, in order to do that, we're actually asking how many pages fit in virtual memory. So we're going to give myself a little more space here to write. We are going to take the size of virtual memory, and we are going to divide that by our page size. And that's actually going to give us 2 to the 32 divided by 2 to the 12, which gives us 2 to the 20 pages are going to be in process P's page table. Because remember, we have one page entry for each possible page, regardless of whether we are using it or not. Now, the next question asks how many of those entries are actually valid. All right. So to compute how many pages are actually valid, we need to figure out how many pages 128 kilobytes is. So we take the address space side, and we're going to divide it by our page size here. Now again, we're making the assumption that the address space is contiguously allocated and that it starts at address 0. So this is going to give us 128 kilobytes, and that's divided by 4 kilobytes. And that, of course, is going to give you 32. So there are 32 valid entries in this page table. Now look at this. Oh, it's a misnumbered page. Oops, or question. So now we're asked to translate these virtual addresses. So we have 0x1a60. Now here's an interesting observation about this. You'll notice I've written it as 1a60. I've dropped all the leading zeros. We sometimes do that, so pay attention that even if we have not written them with the leading zeros, they're still technically there. But let's put them back for now, because they're going to be useful for us. In order to translate this address here, I need to know how many bits I need for my page number. Well, good news, you have all the information. It is the log of the number of pages. So the number of bits for my page number is the log of 2 to the 20, which means I need 20 bits for the page number. Now 20 bits is 4 times 5. So my page number is actually going to be the first 5 hex digits of my address, because that corresponds to the upper order 20 bits. So the page number for this one is page 1. And then I look up in my table at page 1, and I see that the frame number is 00235. So I'm going to translate this by dropping the frame number in and then putting the page offset at the end. And there we go. I didn't have to do any multiplications, and I didn't have to do any crazy modulos, so that's really nice. All right, let's move on to the next address. So the next address is 00 FB5. So again, the highest order 20 bits, corresponding in this case to 5, hex digits is going to be my page number. So my page number for this address is actually 0. Now I look up at page 0 and I see 234 is my frame number. So I'm going to get FE5. That's not too bad, right? That's actually quite easy when you do this method. And then our last address (4664), I'm going to get my page number is page 4. And then what's really interesting is when I look up page 4 in the page table, I see it maps to frame number 4. So my physical address here is actually the same as my virtual address. And that is totally possible. You can absolutely have a physical address identical to the virtual address. Probably doesn't happen too often. All right, now the last question here is asking about if the page size was 16 kilobytes instead of 4 kilobytes, how many entries would be in the page table, how many bits would be used for the page offset, and how many would be used for the page number. So let's take a look at that. So it's easy to note that 2 to the 12 is equal to 4 kilobytes. So 2 to the something is equal to 2 to the 2 times 4 kilobytes, of course, which is going to equal 16 kilobytes. So we end up with our page size is 2 to the 14 kilobytes. So what that's going to mean is that the number of page table entries in the table is 2 to the 32 divided by 2 to the 14. So instead of 2 to the 20, we're going to get 2 to the 18, which means we use 18 bits for the page number, and we are using 14 bits for the offset. And there you go. That's all the solutions to these problems. Now, we actually gave you a second handout here, so let's go to that one. The second handout is called multi-paging. It's a little bit harder than that one. Just trying to get it at a nice size so everybody can see it here. Here we go. So the first thing we note is that our virtual and physical addresses are now 64 bits, and our page size is now 1 megabyte, or 2 to the power of 20 bytes. So, and it's also listed the size of a page table entry. We've also made mention of the fact that each individual page table has to fit in a single frame. Now we're asking the questions, how many bits of each virtual address are needed to represent the page offset? What is the maximum number of entries in an individual page table? What is the number of levels that the page table is going to need in order to do the translation for this system, and so on. So let's start with the first one. We want to know how many bits of each virtual address are going to be used to represent the page offset. So I'm going to go to a new page here. Let's get some nice lines. There we go. So let's do question 1 here. We have virtual memory is 2 to the 64. We're going to divide that by the page size, which is 2 to the 20. So that means that Sorry, I'm answering the totally wrong question. This is asking you about how many bits you need for the page offset. So the page offset is actually the log of the size of the page. So we need 20 bits. That's not bad. Sorry, the question I was trying to answer is how many pages fit in virtual memory. All right, so we know how many bits we need for the page offset. Now we want to know how many page table entries will fit on a page. So what you're going to do is you take the page size and you divide it by the page table entry size, which is going to be provided to you. And that gives us 2 to the 20 divided by 2 to the 4. So that means that we can fit 2 to the power of 16 entries per page. All right. Now, question 3 wants to know how many levels we need. Well, if you had the formula from last class, the number of levels is equal to the number of bits we use for the virtual memory address minus the offset bits divided by the page bits, which is just going to be the log of the number of entries that fit on the page, and then we take the ceiling of this. So let's actually do this little calculation here. So we've got 64 minus the number of bits we needed for our offset was 20. And the number of bits that we need for our page number is the log of the number of entries that fit on the page. So that's going to be, of course, 16. So we have 64 minus 20 divided by 16, and we're going to take the ceiling of that. And the answer that you should get out of this is we need 3 levels. Now, the interesting thing here is that it's not, each of those levels is not going to be full. That is, we're not going to be able to use all 16 bits for each level's page index. That's okay. The thing that you're not allowed to have is a page table that's bigger than a page. But you are allowed to have page tables that are smaller than the page. So what I like to do is I actually arrange this particular address. So if this is the 64 bits, what I do is I say, okay, here's my offset, which is 20. Then I take 16, I take 16, and then whatever's left I put here, which I believe is 12. My adding could be wrong. So that's how I do it. Don't worry about how I've laid this out. If we ask you a question about how many bits are used for each level, we would tell you what kind of scheme we want you to use when it doesn't divide up evenly. This diagram is actually going to be really helpful for the last question, which is actually the hardest part of this particular page. So I'm going to stick that right there, and then I want to give myself some space with one note here so that we can actually do this. So the last question is asking, it says, we have a process that uses a contiguous 128 megabytes of virtual memory starting at address 0. And we want to know how many individual page tables at each level of this 3-level tree do we need in order to represent this address space. Okay. Now, I'm going to tell you what the answer is. The answer is 1 at the root, because you only have one root to a tree. That part should make sense. But there's also only 1 in the next level, and there's only 1 in the level after that. And that's it. Now let's see how I arrived at that answer. So I'm going to redraw this memory diagram here because it needs to be a bit neater to show you how I arrived at this particular answer. I'm not very good at drawing straight lines, by the way. Especially not on one of these tablets. So my offset is 20 bits. And then I've got 16 bits for this level, I've got 16 bits for this level, and 12 bits for that level. And that adds up to a 64-bit address. Now, one of the things they make note of in the question is that the address space uses only the first 128 megabytes, starting at address 0, which means that the only bits of the virtual address which are not 0 is going to be the final 27 bits. So all of the bits at the front of the address are all going to be zeros, and only the last 27 bits may be non-zero. Now, I'd like to point something out here. Let's use a nice highlighter. Let's use a good mathy pink. That means that if my lower 27 bits are non-zero, then of my address, those 20 bits could be non-zero, and they correspond to the offset. And then some number of bits of this level will also be non-zero. And the number of bits here, which will be non-zero, is going to be 7. And this is my 27 non-zero bits. Now, because those are my only non-zero bits, I know that all 12 of the highest order bits for every address in this address space are all zeros. And because I know they're all zeros for every address in this address space, I know that I'm only using one entry in the highest order table. I couldn't possibly be using any more. So, in the highest order table, I've got one root table, and since every valid address would have those 12 bits 0, I only have one valid entry in that one table. Which means that in the second level, since I only have one root table containing one valid entry, then there's only one pointer to a table in the second level, which means there's only one table in the second level. And since I know all 16 of those bits for every valid address are 0, I know there's only one entry in it. Which means that I know there's only one table at the third level. But I know that 7 of those 16 bits are used, which means 2 to the 7 valid entries in that last table. What I'd like to point out is that the number of tables multiplied by the number valid gives you the number of tables in the next level. So try to repeat this, but instead of having an address space with 27 bits used, why don't you try one with, say, 51 bits and see if you can figure out how many tables would exist at each level and how many valid entries there would be. All right, so that concludes our sample problem time. And now for something completely different. No, just joking. Not completely different. All right. Going back to our main notes here, we ended last class looking at a summary of the roles of the kernel and the MMU. Just to reiterate, the MMU, the hardware, is only responsible for doing the actual address translations and raising exceptions. It doesn't do anything else like management of its registers. It's not going to handle exceptions. It simply raises the exceptions and performs the translations. It's the kernel's responsibility to do everything else. So when we have a context switch between threads of different processes, we're going to have to update the MMU's registers with the new processes, page tables, and so on and so forth. And it's the kernel's responsibility for creating the page table and managing the page table, allocating the memory, freeing the memory, and handling the exceptions raised by the MMU. But, you know, we have a bit of a problem. So this is normally in a classroom where I'd start walking across the room like kind of a weird person. We can't do that right now, but I'll describe why I was doing that. So let's look at the computer you have sitting in front of you. Chances are the number of levels used in its page table, and multi-level paging is what we standard use by default these days. Chances are the page table being used on your computer right now has 4 levels. 4. Now, our MMU contains a single register, and that's the page table base register. It's just the address of the directory. What we're going to do then, in order to translate an address, is we extract our first set of bits, and using the page table base register, we're going to go to memory, walk off to memory, we get the address, that page table entry, and we bring it back to the MMU. And the MMU sees, okay, it's valid. And, oh, here's the address of the next level page table. And so the MMU goes back off to memory. And it grabs the page table entry for the next level table, and it brings it back to the MMU. And the MMU sees that it's valid, and then the MMU says, oh, well, this is just a page table. It's not actually a frame number. And so it goes off to memory a third time. And it brings back another page table entry. And then it's going to say, oh, wait, this is also a page table address. Well, it's valid, so let's go again. And so the MMU goes one more time, sends that request to memory, and finally gets back a page table entry with a frame. So in order to do a singular address translation on the computer sitting in front of you, we actually have to go to RAM a minimum of 4 times. 4 times. Now that may not seem like a big deal to you, but memory operations are very, very slow. They are orders of magnitude slower than doing something with, say, a register. Now here's something else to think about. Let's suppose that you have an array. As you know, in C, arrays are stored contiguously in memory, which means that if I have an array of 100,000 items, there's a very high probability that that array lives entirely on a single page. And if it doesn't live on one page, it lives on a block of contiguous pages. And if I'm actually trying to modify the contents of that array inside a for loop, then what I'm going to do is I translate the address of the first index in the array. 4 trips to memory to translate the address. And then for the next element of the array, which sits on the same page, I'm going to go to memory again 4 times to translate that address. And for the next one, and the next one, and the next one. Well, I keep translating the same address over and over and over again. That doesn't make any sense. It's really slow, actually. What I want is the ability to cache these page table entries locally on the CPU so that I can reduce the number of times I have to go to physical memory. And that's exactly what your MMU does. Your MMU has a special cache called the Translation Look-Aside Buffer, or TLB. It is a cache. It is on board, which means it is both faster but closer. And the TLB is going to be very, very small, but what it is going to be used is as a dedicated cache for those page table entries. And so the idea then is that instead of going to RAM to get my page table entry, I first ask the TLB, hey TLB, do you know the mapping? And if the TLB says yes, then I didn't have to leave the CPU. And that is going to significantly improve our performance. So here is the rough idea of how a TLB is going to work. Now, this particular implementation here is known as a hardware managed TLB, and I'll explain that in a minute. So what's essentially going to happen is when the MMU receives a virtual address, it's going to look in the TLB for an entry for that given page number, and if it finds it, it's going to return the frame number, and the MMU can actually perform the translation. That's called a TLB hit, because the thing you were searching for was in the cache, and everybody's happy. Now, if it's not in the TLB, we call that a TLB miss. And what's going to have to happen is when it's not in the TLB, then the MMU is actually going to have to go to memory, and it's actually going to have to traverse that multi-level table to extract the actual page table entry we need. Then it's going to have to add it to the TLB. And the problem is, since the TLB is a cache with very few entries, we may have to actually evict an older entry or some other entry in order to make space for the new one. And then we return the frame number, and we can actually perform the translation. Now, this, I said, is called a hardware managed TLB because it is the MMU, the hardware, that is going to handle the TLB miss. It's going to go and get the page table entry, and it's going to perform the task of actually doing the eviction. Now, this is fast, don't get me wrong. This actually works really well. It's really fast, but there's a downside to this. The downside to this is that your MMU is now going to have to understand the format of your page table, which means that the architecture is going to be dictating to the operating system exactly what the format of the page table has to be. And that means that your operating system can't be overly flexible. I don't know about you, but I don't like being told what to do. Really don't like being told what to do. So another implementation is called a software managed TLB. And in a software managed TLB, when we get a TLB miss, that is, the thing we are searching for is not in that little cache, instead of the MMU trying to solve the problem, the MMU raises an exception and lets the operating system handle the problem. So what's going to happen is when your operating system receives that TLB miss exception, the kernel has to figure out what frame number that address should map to. So the kernel is going to traverse the page table. The kernel is going to extract the appropriate page table entry. The kernel is going to add that entry to the TLB itself, and the kernel is going to perform any eviction from the TLB if necessary. It's a little bit slower, but it's a lot more flexible. Much, much, much more flexible. Now, you'll note here that after the miss is handled, the instruction which caused the exception is retried. So what's going to happen is when there's a TLB miss, we are not going to perform the translation ourselves. We're actually going to force the machine to simply redo it. And this time when it does it, it will actually succeed. And by the way, this is actually how SYS161, our MIPS processor, actually does things. OS161 is a software managed TLB, as you might have noticed if you got that TLB miss exception. All right, now, does that really help? Yes, it does. What does our MIPS TLB entry look like? So first off, our MIPS TLB is actually relatively small. It can only hold 64 entries. Each of those entries is 64 bits in length. It's actually 2 words. And the format is as follows. So our page table entry has the high order word, which is going to have the highest 20 bits as being the page number. And then the low order word, the highest 20 bits of it, will be the frame number. Now, you'll notice that there's a lot of space in here we're not using, and that's okay. After our frame number, this is where we have all those other little bits of information that we might need in our page table entries, such as the valid bit, write permission, and so on. Something you will notice exists in our TLB entry, but we've marked as not being used, is the PID. Now, I'd like to talk about this a little bit because it's actually kind of interesting, and this has changed very, very recently in OS and architecture design and development. So You'll note that when we have a context switch between processes, the kernel is responsible for updating the MMU with the new register values to perform whatever translation is needed for that new process. Part of that is clearing the TLB, because the TLB would contain all of the entries for the previous process. And if we tried to use the previous process as page to frame mappings for the new process, we're going to have a really, really bad time. So when we do a context switch, in addition to updating the MMU with the new register values, we also clear the TLB. And that is the infamously bad named function in OS 161, ASActivate. That clears the TLB. Here's the problem though. Let's suppose I'm rapidly switching back and forth between process A and process B. And let's suppose that neither process A or process B adds many things to the TLB because they're very, very small processes. Their address spaces don't contain many frames. Well, each time that I run those processes, my TLB would start out as empty. And so to start out with, we're going to have to populate the TLB, which means we're going to be making lots of memory accesses. Wouldn't it be nice if the next time a process ran, some of its TLB entries were still in the TLB and we didn't have to start from scratch? There's actually a name for that, and that's called cache affinity. Our MMU's TLB has no cache affinity, but you know what? It would be really handy if we had it, because we would start out in a better state. We could squeeze a little extra performance out of this. But in order to do that, page table entries have to be identified not just by the page number, but by which process they belong to. Hence, the PID field in the TLB entry. And it's not just MIPS that has had this field in its TLB entry format since like the early 90s, but AMD and Intel have also had this PID field in their TLB entries as well. And nobody has used it until very, very recently. And in fact, I think it really only established popularity right around the time of Spectre and Meltdown because it adds extra security. What would happen now, what we do when we use this is the architecture, the CPU has to know which process is actually making the memory request. So maybe it has some extra registers to keep track of which process is currently running. And then when we ask the MMU to perform a translation, it doesn't just check the page number. It's also going to compare the current running PID to the PID listed in the TLB entry. So it gives you some added security, but it also gives you cache affinity, which is a really nice thing. And it's only been used very, very recently. We are not using this field. All right. So that kind of concludes our discussion on paging. As we've said, just to wrap up, it is going to eliminate external fragmentation, but not internal. Although the small amount of internal fragmentation that may occur, we're not going to care about too much. It's not a big deal. A few kilobytes of lost space or simply unused space is irrelevant on a system with 32 gigs of RAM. Now, remember that multi-level paging is going to create smaller page tables most of the time. It's not a guarantee. And that page table will have a higher percentage of valid entries than its single level table for the most part. Of course, that's going to increase the number of memory accesses that we have per translation, which is why we introduced the TLB to actually add a cache to reduce the number of times we need to go to memory. So that is our paging in a nutshell. Now, if you're curious to know a little bit about the history, paging has actually been around since the late 1950s. This is not a new idea by a long stretch. That doesn't mean we had the hardware or software to support it back then, but the original papers are from the late 50s. Now, as I mentioned before, we currently use 4-level paging, but Linux has actually introduced support for 57-bit virtual addresses, which would actually require 5 levels of paging. Now, we have a question on Twitch. How do we decide what a good size for the TLB is? So this is going to have to depend on the architecture. So that's going to depend on how much space on the CPU do you want to dedicate to the TLB cache. You'll have to ask yourself, how much RAM are you anticipating your users to install? What is the average size of a program? How frequently are we going to do process swapping? So there's lots of different considerations that would go into the discussion of how big do you make the TLB, but generally speaking, these are actually kept really small. And if you actually look at like the size of the L1 and the L2 caches on CPUs, they're still really, really small, especially when you consider how big physical memory is and how big your actual secondary storage is. And yet it works just fine. And that's typically because we tend to reuse a lot of values over and over again, if you actually were to do some analysis of how programs execute. All right, so we still have plenty of time in today's episode, so I'd like to take a few minutes then to discuss how exactly virtual memory is implemented in OS 161. So virtual memory in OS 161, first off, MIPS uses 32-bit physical and virtual addresses, which means you can have up to 4 gigs of physical memory and up to a 4 gig address space, theoretically speaking. In reality, our simulator actually only supports 1 gigabyte of physical memory, but if you consider it's a toy operating system, that's plenty. My first computer only had 256 kilobytes of physical memory, and it was on a board this big, so, you know, a gig is a lot. MIPS, we are using a software managed TLB, so every time there's a TLB miss, the MMU will throw an exception. And all of the TLB exceptions, as you might have noticed if you've had some problems with A2A, are handled by a kernel function called vmfault. So your hardware technically uses paging. So the MIPS R3000 is a paged MMU. So our MMU is going to have a singular register with a pointer to it, known as the page table base register. But OS 161 actually uses segmentation. Now you might be wondering, how did we shove segmentation down the throat of an architecture that's using paging? Actually, it's quite simple. So all we did was, technically speaking, our address space is divided into pages, but the pages for each segment are contiguously allocated in virtual memory and also contiguously allocated in physical memory. And when you make that particular decision, you effectively have segmentation in a paging environment. And our translations now become kind of segmentation translations when the kernel is handling the exceptions, even though on the MMU they're actually being handled as paging translations. So our kernel is going to do things with segmentation and then convert it to what page is this on. All right. You're going to fix this, by the way. So here is the address space structure. Some of you may have opened this up. It's in like addrspace.h in the include directory. You will note that the address space structure has 7 fields to it. And there are 3 segments to our address spaces in OS 161. We have a code segment, a data segment, and a stack segment. And in our address space, we actually keep several things for each of these segments. First off, we keep for the code and data segment what's known as the base virtual address of the segment. So this is where in a virtual memory does this segment start. And since our MMU is actually a paged MMU, you can note that the address where the code segment starts will be divisible by the page size. If it's not, the kernel will throw a panic and get very angry. So we have the base address for the code segment, and we have the virtual base address as well for the data segment. And again, that's going to be page aligned, so divisible by the page size. Then we keep track of the base physical address for the code segment and the base physical address for the data segment and the base physical address for the stack segment. So that is, what is the frame address for the beginning of this segment in physical memory. Because in order to do the translation, we need to know where does the segment actually map to. So we've got the physical bases. And then you'll notice we also have the size of the segments, but instead of keeping the size in actual reality, we're actually using how many pages does this segment occupy, because we're going to make the assumption that the segment occupies a whole number of pages. So we've got the virtual and physical base addresses along with the size of the segments. Now you'll note for the stack segment that we only list the physical base address. We don't list the virtual base address, and we also do not list the size. And the reason for that is in OS 161, the stack's base address and the stack's size are constants. Well, actually they're defined, but we'll say the same thing here. And so they cannot be changed. And there's no point in each address space keeping track of the stack size and the stack space address if they're the same for every process. So we're not going to do that. So there's your address space structure. It's fairly straightforward. Now, how do we actually do the translation? So let's suppose there's a TLB miss. This block of code here is actually taken directly from a file called dumbym.c, and this is right out of the VM faults function. And what we're going to do is we're going to figure out what is the top address of each, or the base address of each of these segments, and what is the top? So what is the low address and what is the high address for each of the segments? And that's the first thing that you see happening inside of VM fault. So we get the low address, that's the base address, and then we get the high address. And the high address is found by adding the base address to the page size multiplied by the number of pages. So that's going to give you the limit. So we've got the base, the low, and we've got the high. So we get that for the code segment, which is base 1 and top 1. We get that for the data segment, and then we're also going to compute it for the stack segment. Now you'll note here that user stack is a macro that is equal to this value down here. And dumbvm stack pages is 12 because the stack size is restricted to 12 pages or 48 kilobytes. So what you actually end up with is the base stack address. So that's going to be the low address in the stack. And then stack top is the high address, which is actually just user stack. Now remember, the high address is not actually a part of that segment. It's the limit. All right, so what we do then is after we've computed the low and high for each of these segments, on a fault, we're going to figure out not what the segment number is. No, we don't do something that nice. What we're going to do is use a big old if statement to figure out which range does this address fall into. So if the fault address falls into the first range, then it is in the code segment. And if it doesn't fall into the first range, then we compare it to the second range. And if it falls into there, that's the data segment. And if it doesn't, then we try the stack. And if it doesn't fall into any of these three segments, then we get an E fault because it is not a valid address. And that's what we do. Now, how do we actually translate the address? Well, what we're going to do is we're going to actually figure out the offset of the fault address within the segment. To do that, we're going to subtract our base from the fault address. That's going to give us where in this segment are you right now. And then we add it to the physical base. So this is actually what we would have done for segmentation or dynamic relocation. Once you know what segment's in, you figure out the offset, which is this subtraction bit here, and then you add it to the physical base. And what's going to happen later on is when we add this to the TLB, which happens later in VM fault, we'll actually convert that to a page to frame mapping. But you don't need to worry about that for now. All right. So in the notes here, it says, let's give this a try. Let's actually try now to translate some addresses for OS 161. So why don't we take our hand at that? Let's look at process 1. So let's scoot this over here and let's bring up a writing area. So we're going to ignore process 2. Let's give a nice new page, nice and crisp. All right, so I can tell you that I know off the top of my head which segment each of these addresses lay in, but that's simply because I have the address space layout memorized for OS 161. So let's start with the first address, which is 400004. Now, I look at this address and I look at the base and the top, and I'm just going to estimate in my head what the top is. But I can tell you that I know this first address falls in the code segment because it is greater than 40 or 400,000, which is our VBase for that one. And it's also bigger than the top for that segment because, or smaller than the top, because 8 pages, that's 8 times 1,000. So that's going to be 408,000 is our top address, and 400,004 obviously falls in that range. So this is going to be code. All right, so that's not that bad. So then what I'm going to do is I'm going to compute the offset. So I subtract from the fault address the base. So I get my offset is equal to 4. And then the physical address I'm going to get is by adding the offset to the P base 1. So that's going to give me 200,004 as the physical address for this one. Not too bad. Now let's look at the next one. We've got 100091A4. Now I look at the size of, so I'm going to look at my first segment, which is the code segment, and it's very obvious that this address is not a part of the code segment. And then I look at the data segment and I realize, okay, this might be the place. So our address is definitely bigger than the base, but is it smaller than the top? And I see that this segment has 16 pages. Sorry, I converted that number to decimal here. So I actually realized very quickly that indeed I am going to have this address is less than the top, which means that this is in the data segment. So I compute the offset again just by subtracting the base address of the data segment. So I get my offset as 91A4. And that's going to then give me the physical address of, looking up at P-base, 8091A4. Not so bad, right? Now the third one. Now the first question we have to ask, because it's not given here, is what is the stack base? The stack base is equal to this calculation here. That is user stack minus number of pages times the page size. So you end up with stack base is that address there. And then stack top is equal to user stack. And I look at this address here and I see very clearly that it falls in that range, which means this is a stack address. So I'm going to calculate my offset as 1A4. And then I can do my physical address looking at the stack P base is going to be 0x10 1A4. It's not too bad, right? It's very reasonable. Now I look at the last address for process 1. It's not in the code segment. It's not in the data segment. And it's not in the stack segment either, because the stack segment's base address is 7FFF4000, and this address is less than that, which means it's not in the stack, which means this address is an exception. All right, so I'd like to let you try process 2 on your own. And that's going to give you some good experience because this sounds like a pretty good question we could ask in those quizzes. All right. So that's how the address translation works in OS 161. Now, how does that address space actually get initialized? Because when you load a program, how are you actually going to populate your address space? How do you know how big to make that address space? Well, all of the information you need to create and populate the address space is actually located in the binary file itself. And our binary files have a particular format called ELF, executable and linking file format, which is something you should be familiar with from 241. Although if you don't remember it, that's totally fine. And what's going to happen is that when we actually load a program, we are going to extract from that ELF file all of the information we need to figure out how big the address space should be, how much memory we need for the code segment, how much memory we need for the data segment, and what parts of the binary file to load into each of those regions of the address space. All of that is in that ELF. So if we actually look at the ELF file, and we will do this actually here in a minute, what we're going to do is we'll actually see that the ELF file has several parts to it. The first part of the ELF file actually is a header. It's a human readable piece of information that actually describes the segments of the address space for the program. So it's going to tell you at what virtual address the start of each segment will be. It'll tell you the length of the segment in the virtual memory. It will tell you where in the binary file you can find the image and how big that image is to be copied into that. It'll also tell you things like, should this be read-only or should this be read-write, and some text describing, what is this? So, we can actually do this if I can remember the command, which is always a good question. Can I remember the command to do this? So let's actually see the contents of our header. So let's do CS350 object dump -h, and let's do sort. Or I guess I want there we go. So here what I've done is I've used object dump to get the header of the information contained in the binary ELF file for the sort program. And what you can see here is it tells you about the format, and then it's going to tell you about all of the segments or sections that can be found in here. So first we see the text segment. That is your code, and it tells me how big it is, and it tells me the start virtual address, and it tells me the offset as where in this file can you find this particular piece of data. It also tells me that when you load this, it should be loaded as read-only program code. Now, what gets included in the text segment in OS 161 is also the read-only data. So that's any global constants. And you'll see here how big it is, where in virtual memory that's going to live. You'll see where in the file you can find that data. And again, load read-only. And then the data segment is down here. You can see the size of it. You can see the start virtual address. And then you can see here that when we load it, this is where you can find it in the binary file. And you'll note that the read-only flag is missing because it's not going to be read-only. So all of the information that we need to create the address space and populate the address space is actually in the binary file. It's pretty cool, right? You'll notice the stack segment is missing. That's a very common thing, and that's usually because the stack pertains to the execution of the program. So there's not going to be any stack information in the binary file because the program hasn't run. It has no running stack frames. And the size of the stack is usually dictated by the operating system, not by the compiler. Not to say that it can't be estimated, but it's not what we do. All right, so that's what our ELF file contains. And then what's going to happen is in a magical function called load_elf, which is actually what loads that binary file, it's going to read all of that header information, and then it's going to allocate the address space, and it's going to allocate the space for each of the segments, and then in load_elf, we will actually copy the contents from the binary file into each of the appropriate segments. And then after load_elf, we usually call asDefineStack to actually create the stack, which should start out as empty. All right. So we've only got about 7 minutes left, but I think that's enough time to introduce the next topic, just very briefly. So we have virtual memory for the kernel. I'm not going to go through all of these slides right now, but what I would like to do is just tell you that it's not just the user program we want in the kernel. Sorry, virtual memory. It's not just the user program we want to use virtual memory. We actually would love it if our kernel was abstracted from the physical addresses too. We want our kernel to use virtual memory, which raises this whole chicken and egg problem. If the kernel is responsible for implementing and managing virtual memory, then how does the kernel also run in virtual memory while it's booting all of these systems? So on the next episode, what we're going to cover is we're going to look at the bootstrapping problem, which is that chicken and egg problem and how it's solved. We're also going to look at the sharing problem, which is if both the user program and the kernel are using virtual addresses, how do you know whether you've got a kernel virtual address or an application virtual address, and how do you figure out how to copy data from one to the other if they're using the same address range? So we're going to discuss how this is implemented with OS 161 and many modern operating systems. And then also in the next episode, we're also going to discuss one of my favorite topics, which is on-demand paging. And we'll have another sample problem as well, which we'll introduce and solve both on the same day. You've had enough sample problems for today, I think. All right, so we will see you next week for episode 15. And don't forget to get those assignment A2As working.
You know the world has changed and nothing's gonna stop it. Turning on connections, the nets kicked on the rockets. Now we're firing up the .nets and the .coms. If you look behind it, you see that sun's providing productivity. It comes from our ability to supercharge the growing net economy. Either have lunch or you'll be lunch. Now's the time to break through, because sun is number one. What can we .com for you? So anytime, anywhere that there's a job to be done, then that's on any device and open to anyone. We don't just lead it, you know, that we believe it. The best has just begun. The dot that's in the .com, yeah. So anytime, anywhere that there's a job to be done, then that's on any device and open to anyone. We don't just lead it, you